Hello. Today we're going to have a lecture on dynamic Stackelberg problems. And this is going to be actually close to a canonical example of an optimum problem in which the optimum decision, the sequence of optimal decision rules are time inconsistent. And there's going to be a telltale sign of this. Oops, time inconsistent. And there's going to be a telltale sign of this. Or signs. One is there's going to be decision rule for time t. That's going to be one thing. And then there's going to be decision rules for times t greater than or equal to 1. So these are going to be different decision rules. There's going to be different decision rules, and there's even going to be different state variables. So these are going to be different sets of decision rules and state variables. And we're going to find out that another way to say this telltale sign is that a continuation of a Stackelberg plan is not a Stackelberg plan. So if we'd looked at a continuation of a plan that we computed using ordinary dynamic programming, the continuation of the original plan would be an optimal plan. But here for the Stackelberg plan, that's not true. And that's a sharp way of summarizing time inconsistency. So we'll see this in full detail as we proceed. Now our tool here is going to be the linear quadratic optimal control, or the linear quadratic dynamic programming. It's still going to be our tool. And this might seem ironic or paradoxical given what I just said. We're going to trick the LQ problem into doing what we want. And the key thing is, the basic idea is we're going to use the LQ problem into doing our work. And the way we're going to do this is we're going to trick the LQ problem basically into solving our problem for times t greater than or equal to 1. And then we're going to stare at it and solve the problem for t equals 0. So we are still going to use backward induction in a thorough way. So that may sound a little mysterious now, but hopefully we'll fill it in. So let's get started. We're going to use linear quadratic because we can compute lots of things and get our hands on things. But I think you'll understand that the basic principles that we're talking about will transcend the linear quadratic setting. Okay, so here we go. Here's going to be our setting. We're going to let ZT be an n, we'll call it nz by 1 vector of natural state variables. So these are These are variables that, like capital stocks, variables that summarize information available to agents, and so on. And then we're going to let xt be an x by 1 vector of endogenous forward-looking variables. So these things, they will satisfy themselves their own equations, and often these are their own Bellman equations. And I'm just using the term Bellman equations freely here to be an equation that expresses xt, this Bellman equation, xt as a function of future things. That's the key thing. And often does it in a recursive way. So I'll give you an example of this in a minute. Okay. So, so it's going to turn out here's kind of a thing. This is MIT type, old-fashioned MIT type language. Is xt forward-looking? Or is xt backward-looking? And one of the themes of this lecture is going to be yes and yes. It's both backward and forward-looking. And this is going to be yes at t greater than or equal to 1. So we're going to fill in the mystery in this statement, these statements. Okay, so here's what we're going to do. We're going to start the trickery. We're going to let yt equal zt xt. We're just going to stack these things in. And for a while, and we have to remember that zt is a natural state variable and xt are these things that are forward-looking. So these are forward-looking. You have to remember that all the time. But we're going to write a return function, a one-period return function. We're just going to write it like this: y prime ry plus u prime qu. And that's going to be our definition. This is going to be, the spirit of this is r and q might be positive semi-definite matrices. Again, we can relax that. And then I'm going to write a maximum problem. So I'm going to say at time 0, there's going to be an agent that we're going to call a government. And for us, the government is also known as a Stackelberg leader. Stackelberg leader. At time 0, this government is going to take x0, I'm sorry, it's going to take z0 as given. So there's an initial condition, but not x0 as given. And here's what it's going to do. It wants to maximize. It wants to maximize. That's what the government wants to do. It wants to maximize this minus our loss function. And I'm going to formulate this as a non-stochastic problem, but we have the full machinery of certain equivalence available. that we talked about in a previous lecture. Okay, so R is going to depend on the whole y vector, and we're going to have this subject to this law of motion. This is going to look a little strange. Well, all right, this is a vector. Here we go. And I'm going to write this A11 hat, A12 hat, this partition A22 hat, A21 hat, A22 hat. Oh, by the way, I'm talking about chapter 19 of RMT4, which you have available. Okay, and then, by the way, this is a mistake, obviously. ZT plus 1, ZT, YT. So this whole, oops, sorry about this, XT plus 1, XT. This is YT. This is YT plus 1. Good, now we're going. Plus B hat UT. So what I submit is my model is going to have this form. Now, if we look at this first equation, the first block of equations, since that's the identity matrix, ZT is feeding back on lag Z and lag X, possibly. But this equation, the second block equation, these are going to be in the form of Euler equations. These are Euler equations for the decision makers who choose XT. So we're going to have in mind that there's some followers who at T actually choose XT. And they choose them according to their own little maximum problems. And those maximum problems give rise to first order necessary conditions that take the form of Euler equations that express XT possibly as a function of current ZT and future XT plus 1 and future ZT plus 1. So the consumption Euler equation might be an example. So now I'm going to assume that this matrix is invertible. That will often be satisfied. If it's not, we can modify what we're doing quite easily to make the rest of the argument flow. So I'm going to assume that that's invertible, and I'm going to rewrite this system like this. I'm going to just take the hats off. I'm just multiplying through by the inverse of that matrix that I've assumed is invertible. And I get this. And then this is going to be a B UT. And what's UT? UT is a vector, should have said this early, of controls chosen by the Stackelberg leader. And these XTs are chosen by Stackelberg follower. That might be, for example, a competitive market. So now I'm going to write this whole system as YT plus 1 is equal to A YT plus B UT, and my objective function is again beta to the T. It's got a minus here, R YT UT. And what's given is not, y0 is not given. What is given is this is given, this is not given. Okay. Okay. So here's the government's problem. The government's problem, we're calling the Stackelberg leader the government. Now you'll notice that this problem looks, except for this x0 not being given, this looks just like a linear quadratic dynamic programming problem, or an optimal linear regulator, we called it last time, except for the fact that x0 is not given. Now, indeed, what the government is going to choose, the government is going to maximize, call this star, by choosing, what is the government actually going to choose? The government's going to choose ut xt. It's actually going to choose xt, zt plus 1, t equals 0 through infinity. It's going to choose this entire thing, including the current xt. Now you could say, wait a minute, but you thought that xt, I already said this, that whole sequence was chosen by the followers. Now I'm saying that the government or Stackelberg leader chooses it. So what's going on? Well, the choice, the optimum choice of the followers, that's completely summarized, we hope. And this is the so-called first order approach. It's completely summarized by their first order necessary conditions, and these are the second block of our original equations. So the Stackelberg leader is constrained by those Euler equations. It just can't push xt around anywhere. But it can move xt around in a variety of ways that respect those Euler equations. So let's elaborate on this a little bit. This is going to be a little digression. Let's take the original block, take the second block of our original equations. Okay, and write them like this. We'll see that it's going to look like, I'm just listing the variables that are in that equation. There's a z, there's everything in sight's a matrix or a vector. There's a zt plus 1, those were both in there. There's a government control, ut, and there's a next period, x. Now, in the problems that we are going to actually confront, phi 0 is typically a stable matrix, or its eigenvalues are at least bounded by 1 over root beta. So this is an equation. This is like the Euler equation for xt. And we could actually solve this equation forward to get the stable solution of it. And it would look like this. It's a matrix geometric sum of what? Future z's and future current and future u's. So this equation is telling us that future u's affect x0, x1 up to xt. This is what this is telling us. Future u's, future values of the government settings. So this is a setting in which these Euler equations are summarizing how the private sector or the followers are adjusting their time t decisions in response not only to current government policies, but future government policies. And we're using rational expectations very heavily here. The entire literature on time consistency and time inconsistency rests heavily on rational expectations. And that's why rational expectations was invented first, and then shortly thereafter, the time inconsistency problem surfaced. Okay, so that's telling you a little bit about what the nature of these constraints are. So what we're now going to give, so again, our problem is the government is going to choose this object, and we want to formulate that. And what we're going to do is we're going to give a recursive formulation of this. Oh, by the way, just a little bit of slang. I'm using language loosely. I'm going to refer to this as a Bellman equation. This itself is a Bellman equation. If you think about it, it's got xt expressed as a function of a bunch of stuff and a future xt. So this is a Bellman equation for xt. Well, I'm speaking loosely. And now we're going to see that this object that itself satisfies the Bellman equation is going to be an argument of another Bellman equation. And that's why we're loosely using this term dynamic programming squared. This is, in this class, is our first encounter with this apparatus. We're going to see it often. Okay, so just a little notation. I'm going to define this thing. I'm going to put this little arrow above this. So this is going to be for any vector AT. I'm going to define AT bar as the continuation of AT, of that sequence. So I'm going to start with an original sequence for any sequence AT of vectors. I'm going to define the continuation at A as just the tail of the sequence. Okay. So we're going to have a definition to be pedantic. So in this notation, given Z0, the Stackelberg plan is to choose. So what are we going to choose? We're going to choose a continuation for X, start the whole sequence for X. We're going to choose a continuation for Z, starting and a U0, the whole plan for Z, U0, to maximize star given the law of motion. subject to, the usual. Here's dagger, dagger. It looks just like what we had in the last lecture. For t greater than or equal to 0. So, definition, a Stackelberg plan, is this Z1 that solves Stackelberg plot problem. Okay. So now what we're going to do is we're going to formulate this problem recursively. So we're going to have two Bellman equations. So the first thing we're going to do is we're going to define a feasible set of Y1 continuation U0 sequences. Remember that YT is equal to ZT XT, that vector. We're going to define this. So what we're going to define this set Y omega Y of Y0. And we're going to see why this is a function of Y0 in just a second. This is the set of continuations that look like this. That pair of continuations subject to YT plus 1 is equal to AYT plus BUT for all t greater than or equal to 0. So stare at that. Stare at that for a minute. So starting from a Y0, which we're taking as given, the spirit of this is we're taking Y0 as given here. And then we have this set of sequences. And now I'm going to define two subproblems. And this is and you can say, well, wait a minute, Y0 isn't given in this problem because Y0 equals Z0 X0. Well, Z0 is given, but X0 isn't. But nevertheless, when I define this feasible set, I'm pretending like Y0 is given. So why am I entitled to do that? It's because I want to. And I'm going to postpone the problem, confronting the nasty problem that X0 is not given. So I'm going to define two problems. I'm going to define subproblem 1. So here it is. Here it is. I'm going to take V of Y0. I'm going to let V of Y0 be the maximum. Now, what's this maximum going to be over? It's going to be over Y1 continuations, U0 continuations, belonging to omega of Y0. And I want to maximize this. That's not the Stackelberg problem, but it is I'm just going to make a remark. It's not the Stackelberg problem. It's a much easier problem. This is a linear quadratic dynamic programming problem. And how do we solve it? It's not the problem we ultimately want to solve, but how do we solve it? Well, I used chapter 5 of RMT4, or our last lecture, and we have the optimum value function is minus y0 prime p y0, where p solves the Riccati equation. That's true of subproblem 1. So the whole trick is y0 is not given, but we're going to pretend that it's given. If we pretend that it's given, then this problem maps exactly into what we had studied last time. It's an ordinary dynamic programming problem. Despite the fact that there are, one of the variables we're taking is given, is being forced to satisfy a Bellman equation through this transition loss that we've constructed for A and B by taking those inverses. So now here's subproblem 2. So subproblem 1, okay, so here's subproblem 2. It's to create a value function. So we're going to let z0 be the optimum value for the Stackelberg problem, the one we really want to solve. That's the one we really want to solve. So wz0 is going to satisfy this. It's going to be the maximum over x0 of v of y0, which we've already computed. So if you think hard, breaking it into these two subproblems does what we want. We're building in that the x's are always satisfying the Euler equation for any initial x. And we did that by imposing the Euler equations are embedded in here. And then we got what the value function would be, v of y0, for all possible values of x0. And then we're having the government choose the x0. So we can solve this problem because we know that the problem becomes, we know that v of y is equal to minus y0 prime p y0. And now we'll just partition. So this is equal to minus z0 prime. We're just going to partition the p matrix z0 minus 2 x0 prime p21 z0 minus x0 prime p22 x0. And all I've done here is partition p conformably with y and x, with z and x. So I've done that. Okay, so now we have this. So now I'm going to choose x0 by equating the gradient of v of y with respect to x0 to 0. And I get this equation. Let's just take the derivative using our formulas for differentiating or, here's our equation, x0 equals minus p22 inverse p21 z0. That's my formula. So z0 is a given state variable. It's a given initial condition for the natural state variables. x0 is the initial value of x0 chosen by the private people. Once we choose that, we have the optimum decision rule. How do we affect that? The optimum decision rule is minus fyt equals minus f1, f2, zt, xt. So we've completely solved the problem. Okay, so a couple things to notice. We stare at this. It might remind us of something. Because reminder from last time, if we think about what the Lagrange multiplier, the vector of Lagrange multipliers on the quote unquote pseudo state variables xt are, they satisfy, remember we had our formula last time. We have our formula from last time, ut equals p, the vector of Lagrange multipliers, pyt, through the gradient of the value function. So this tells us, if we just partition, that mu xt, that's the shadow price of xt. And if we substitute this in, we'll find that mu x0 is equal to 0. So the advice is set the shadow price equal to 0. But what you'll find at time 0, you will find that mu xt does not equal 0 for all t greater than or equal to 1. So this is a situation where in mu xt has an interpretation. It's the cost to the Stackelberg leader of delivering the planned or promised XTs to the followers. That's what it is. So what's gonna happen is if we take our decision rule, we can write the final closed loop system, what we did last time doing this. We would have, if we write out the second piece of this, we would have xt plus 1 is going to evolve according to, I'll just write this, I'm going to write this as a partitioned. If I do the appropriate partitioning of this, a minus bf, I'll just write this all out, of zt plus a1, a minus bf, the partition of that 2 times xt. This is telling us how the Stackelberg leader takes the value starting from 0, takes this value and updates a future x, and then the decision rule that the Stackelberg leader uses at time t is f1 zt f2 xt. So it's feeding back on this xt. So for t greater than or equal to 1, the decision rule, this is true for all t greater than or equal to 1, whereas for t equal to 0, it's equal to this. So these are different decision rules. The planner uses a different decision rule for t greater than or equal to 1, the Stackelberg leader for t greater than or equal to 1, than for t equal to 0. And this is a telltale sign of the time inconsistency. Because, and I want you to think about this, a continuation of a Stackelberg plan is not a Stackelberg plan. So I want you to think about that. And ultimately the answer is this is not this. So just to summarize, the Stackelberg plan, we have the following timing protocol. This is all about timing protocols. At times t greater than or equal to 1, the government takes xt, zt is given, and chooses, this is our sequential interpretation of this anyway, chooses that. Chooses a u for this period, it chooses a z for this period, and it chooses xt plus 1 for next period. At t equals 0, the government just takes z0 is given and chooses x0, u0, z1, and x1 is given. So it's choosing different things. In particular, it's choosing at time t equals 0, it's choosing something which In future periods, it takes as given. Okay, so I think you're equipped to read the rest of this chapter, chapter 19. Read it slowly. You're also equipped to use Python or MATLAB and solve problems like this. So chapter 19 has several examples. It's got an I/O example. It's got a large firm with a competitive fringe. It also has some simple macro examples in some of the exercises. So this is our first encounter with something we're going to see over and over again, this dynamic programming squared. And where it surfaces here is right here. Inside this Bellman equation, there's a variable, x0, which itself is satisfying a Bellman equation, which is embedded in the law of motion that we've substituted. We've managed to press into this form. When we study other applications, the computations are going to be significantly more complicated because we're going to move outside the linear quadratic framework. But you're going to see a similar structure in terms of a difference between a time zero problem and a time one problem. So this concludes today's